In this video, I will be discussing about covariance and correlation for positive relationship between two quantitative variables. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. And this relationship can be measured by a statistical value called a linear correlation coefficient, which is denoted by R. And this R measures the direction and strength of the linear relationship between the two variables. While a covariance is one of a family of statistical measures used to analyze the linear relationship between two quantitative variables. Take note that this covariance value is easily affected by scale of variables, which means that if you multiply the variables by some other constant, then the value of the covariance is changed. Now, this correlation coefficient R is simply a normalized form of covariance. They are otherwise the same and are often used semi-interchangeably in everyday conversation. Hence, both measures describe the relationship between two quantitative variables. Now, to illustrate this one, allow me to use an example about relating the two variables, say study time and the test scores of 6 students. So this first student A allotted 5 minutes in his or her study time that gives him or her a score of 80. And the second student allotted 24 minutes study time which gives him or her a score of 89. And so on and so forth for the 6 students. So first let us compute for the mean of the study time, which we denote here a variable x. So the mean of the variable x is equal to the sum of all values in x divided by how many of them. And if you add 5 plus 24 plus 15 plus 10 plus 5 plus 25, it gives you a sum of 84. So this is 84 divided by 6. And 84 divided by 6 is 14. So we know that the mean of the variable x is 14. However, for the mean of the variable y, we have the sum of all the values in y divided by how many of them. And if you add 80 plus 89 plus 85 plus 84 plus 82 plus 90, gives you a sum of 510. So this is 510 divided by 6. And if you divide these two numbers, it gives you a quotient of 85. So we know that the average of all test scores is 85. Now we can compute for the deviation of each value in x from the average of 14. So we have here 5 minus 14. So subtract each value by its mean. And also 24 minus 14. And here 15 minus 14. Also this one is 10 minus 14. And we have here 5 minus 14. And also 25 minus 14. And if you subtract 5 by 14, gives you a difference of negative 9. And also this one, 24 minus 14 is 10, and 15 minus 14 is 1, and 10 minus 14 is negative 4, and 5 minus 14 is negative 9, and we have 25 minus 14, it's 11. Now we can square these differences from the mean here. So the square of negative 9 is 81. The square of 10 is 100. The square of 1 is 1. The square of negative 4 is 16. And the square of negative 9 is 81. And the square of 11 is 121. So with this one, I can compute for the variance of the variable x. And we know the formula of the variance, which is the sum of the square deviations of every value from its mean divided by n minus 1, because we consider this one as a sample of all the students. So if you add 81 plus 100 plus 1 plus 16 plus 81 plus 121, we have a sum of 400. So this is equal to 400 divided by 6 minus 1 because there are 6 students here. So this is equal to 80. So we know that the variance of the variable x is 80. Also, we can compute for the variance of the variable y here. And the formula for the variance for the variable y is the sum of the square deviation for every value in y from its mean here, divided by n minus 1. So if you subtract 80 by its mean, which is 85, so you can have subtracted this 80 by 85. And also next, which is 89. 89 minus 85. And we have 85 minus 85. And also 84 minus 85. And 82 minus 85. And lastly, we have 90 minus 85 here. Now you can get the difference here, which is negative 5, and this is 4. The difference here is 0. The difference here is negative 1, and this one is negative 3, and this is 5 as a difference. And if you square these differences from its mean, we have 25, because this is the square of negative 5, 16 is the square of 4, 0 is the square of 0, and 1 is the square of negative 1, 9 is the square of negative 3, and 25 is the square of 5. And if you add all of this, you've got a sum of 76. So the sum of the square deviations of every value in y by its mean is equal to 76. And if we divide this one by 6 minus 1, we've got a quotient of 15.2. So this one is the variance of the variable y. So therefore, we can compute for the covariance of the variables x and y. And we know that the formula is equal to the sum of the product of the deviations from its mean divided by n minus 1. Because again, we consider the 6 students as a sample from all students. So we just multiply these differences by these differences here. So we have negative 9 times negative 5, which is 45. And we have 10 times 4, which is 40. And we have 1 times 0 is 0. And negative 4 times negative 1, it's 4. And we have negative 9 times negative 3, it's positive 27. And 11 times 5, which is 55. And if you add 45 plus 40 plus 4, 27, and 55, you've got a sum of 171. So the value of the covariance is 171 divided by 6 minus 1. And the quotient between 171 and 5 is 34.2. So this is the covariance value between the two variables x and y, which are the study time and test scores of the 6 students. Now we can compute also for the correlation coefficient between the two variables, and the correlation coefficient between the two variables is the covariance between these two variables divided by the product of the standard deviations of the two variables. And to compute for the standard deviations of the two variables, we need to find the square roots of these variances here. So this is actually the square root of the variance of x. And this is multiplied also by the square root of the variance of y. And we know that the covariance between x and y is 34.2. And this will be divided by the square root of the variance of x, which is 80, multiplied by the square root of the variance of y, which is 15.2. And if you are going to multiply these two numbers here, we have 8 times square root of 19. And if you get the quotient of these two numbers, you've got a number of 0.98, which is the correlation coefficient value between x and y. Now take note that the covariance, which is 34.2, and the correlation coefficient R, which is 0.98, are both positive, this gives you an idea that the relationship between the two variables is positive, which means that they are directly related, meaning that as the study time increases, the test score increases also. But when the study time decreases, the test score decreases. So they behave in the same way at the same time. So both the covariance and the correlation coefficient gives you the idea of the direction of their relationship. But only the correlation coefficient gives you the strength of the relationship and not the covariance value, because we've mentioned that the covariance is easily affected by the scale of variables, which means that if you multiply, say, a number 5 to the variable x, the value of the covariance changes to a higher value, but the correlation coefficient doesn't change. That's why we said before that the correlation coefficient R is simply a normalized form of covariance because we divided by the product of their individual standard deviations. Now, to see that one graphically, we need to use a very useful graph for displaying the relationship between these two quantitative variables, the study time and their corresponding test scores, in a scatter plot. The values of one variable appears in the horizontal axis. Say this is our study time axis. So we have 5 minutes, 10 minutes, 15 minutes, 20 minutes, and 25 minutes, and here 30 minutes. So this is our study time. But to our y-axis, we have here the test scores. So let us now plot the points. So the study time of 5 minutes gives you a score of 80. So that one here is our data point for a student A. And for 24 minutes study time gives you an 89 as a score. So we have here 24 and this is 89 here. So this is for the student B. And we have 15 minutes gives you a score of 85. So 15 minutes gives you a score of 85. So this is our student C data point. We have also student D, which is 10 minutes. So we have student D allotted 10 minutes and it gave him a score of 84. So it is here, and this is our student D. And we have 5 minutes gives you a score of 82. So it's here. This is our student E. And lastly, a student who incurred 25 minutes as study time gives a score of 90. So this is our student F. So that is our scatter plot of the 6 students here in terms of their study time and test scores. Now you notice that the points form a pattern that is approximating a straight line. And we can draw here a line that best fits all the data points here. So this one here. So this line is what we call a regression line. So using a scatter plot, you can visually see the behavior, the pattern between the two variables, that as study time increases, their score also increases. But as their study time decreases, their score also decreases. They behave in the same way. So that is a positive correlation. And statistically, we can determine the direction of the relationship that it is positive not only using the scatter plot, but by computing the R value. And we have here the R value of 0.98. And that is very close to positive 1, then therefore, it has a positive relationship. And so with the covariance, it has a positive value of 34.2. Then both of them gives the direction of the relationship, that it is positive, that they have a direct relationship. But only the R value gives you the strength of the relationship, because this is a standardized or normalized form of a covariance. But the covariance cannot give you the strength of the relationship because this value increases as you multiply one variable by some number. So in summary, covariance and correlation coefficient gives you the direction of a relationship. And in this example, both are positive, so the relationship is positive, meaning they have a direct relationship. But only the R value gives you the strength and not the covariance because correlation coefficient ranges from -1 to 1. So the closer the values to -1 and 1, the stronger is the relationship. But the closer the value to 0, the lesser is the relationship. However, for the covariance of the two variables x and y ranges from -infinity to positive infinity. Therefore, it will not give you the idea of the strength of the relationship, only the R value. But since our covariance is positive, it gives you the idea that the relationship is positive. And so, this is a good place to stop. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.